Yeah, my name is Matthew Jané. I'm a graduate student at the University of Connecticut. Today I'm going to be talking about my book, Artifact Corrections for Effect Sizes. It's essentially an online, open access, open source book related to artifact corrections. Study artifacts are really any source of methodological contamination that induce bias in research findings. Here, things like sampling errors and random errors are not really relevant for my definition of artifacts, but it's really any source of contamination. Now, hopefully one day we get to a point where we won't need artifact corrections because methodology is done perfectly, although maybe that day won't come. But for right now, artifact corrections provide a temporary band-aid to some of the methodological flaws we see in studies. So just a little bit of a sort of preliminary thing about this book. It's a living textbook, so I'm going to be upgrading the book continuously with new features, new visualizations, new content, or maybe also changing content that might have had errors in it or anything that like that. So let me show you guys one feature of this site is called Hypothesis, which allows you to comment, annotate any parts of the website. So you can highlight and annotate parts that you think that there's an error, or you might want to suggest an edit or a new feature. You can use Hypothesis. So it's a collaborative website. Obviously, I'm going to be filtering any comments that go through and make changes as necessary, but it's your opportunity to contribute to the book. And I have a list of contributors. So if you do want to contribute to the book, feel free to make those annotations. And I want to thank the contributors that have made those edits so far, especially my advisor, Blair Johnson, who's helped pretty much conceptualize the project, reviewed and edited it. Also, Christopher Rhodes and Elizabeth Schifano, my co-advisors, who also helped in reviewing and editing, as well as Ed Kroc, who I think is in the crowd. He was super helpful because I was able to bounce questions off him that are way beyond my mathematical level. So he was also very helpful. And also thank you to everyone else who's contributed so far. So let's get into the book. So I'm going to do essentially a speed run of the content of the book. Hopefully I can get it done within the time frame. So the first content chapter is on random variables and expectations and probability distributions. So this is probably the densest chapter of the whole book because we are essentially building up the foundation of all these artifact corrections from sort of like measure theoretic principles. I'm a beginner in sort of measure theory, not sort of like abstract mathematics. So I have been reworking this chapter many, many times. And again, Ed Kroc was a huge help, especially in this chapter. So I'm going to kind of briefly skim through this chapter and just tell you some major things. So like here we're defining random variables. So like what are random variables? Also, what's measurement error? So oftentimes in studies we have this true random variable of interest, but we only have access to observed scores or like proxy scores that we can use as measurements of this phenomenon, of this random variable of interest. So measurement error, essentially, we have this, we have a y tilde, which is our observed measurement, observed random variable, which is a proxy for a true score, which is just denoted as y. So that's sort of like just basic, like what is measurement error and how does it relate to the variables of interest? So we also talk about probability distributions. And I don't think I need to go through this too much, but essentially just defining what a continuous probability distribution looks like. What does a Bernoulli distribution look like, where random variables take on a value of either 0 or 1. And then a more important chapter was a more important section of this chapter is study samples. So oftentimes in studies, we have a population of interest. And this population could be like, for example, college students, the population of college students in the United States. But then our study population is usually some subset of that population that the researcher actually has access to. So like, let's say I have access to freshman students at the University of Connecticut. That's my study population, which is different from the composition of that population is different from the population of interest, which is all college students. So it's the set of eligible individuals that the researcher can sample from. Now, a study sample is a random sample of the study population. So it's not necessarily a random sample of the population of interest, but it's a random sample of the study population. That'll be important when we talk about selection effects. Then we talk about conditional expectations, invariance of random variables, as well as covariance. And that's just defining conditional expectations, means, sample means, variance, sample variance, etc. That allows us to actually compute effect sizes. So that's sort of a brief introduction to that chapter. Again, this chapter is the densest chapter that there is, but you could probably move past that chapter and not lose too much. This chapter 4, talks about effect sizes and artifacts. So this is just a brief introduction to 2 primary types of effect sizes that are the subject of this book. So the effect sizes are correlations and standardized mean differences. I hope in the future to add unstandardized mean differences, as well as regression coefficients and odds ratios. But as of right now, it's just correlations and standardized mean differences. And broadly, effect sizes are a parameter that describes the degree of association between 2 random variables. So for a correlation, you might be looking at 2 continuous random variables. It doesn't necessarily have to be continuous, but let's just say 2 continuous random variables, X and Y. The correlation is essentially the standardized covariance between X and Y. Yeah, that's the population correlation. This is just a figure demonstrating a positive and negative correlation. Standardized mean differences are when we want to look at average differences between 2 groups. So this is especially useful in meta-analysis, where, well, both correlations and standardized mean differences are standardized effect sizes, so they can be comparable across studies. But for a standardized mean difference, we're looking at the difference between 2 groups, the means of 2 groups. So if we have group 1 and group 0, the mean difference is the mean minus the mean of group 0. The mean of group 1 minus the mean of group 0 divided by the within group standard deviation. This is just an illustration of 2 distributions showing a standardized mean difference of 0.75. Here's an example of just a sample correlation. So this is an example we'll come back to later on in the book, especially when we talk about selection effects. So in the United States, there's 2 sort of major college admissions tests. You have the Scholastic Achievement Test, or the SAT, and the American College Test, or the ACT. So because they're both standardized assessments assessing student or academic performance, they're going to correlate very highly with one another. And so they do in this sample of, like, I think about 1,000 individuals. This is real data, by the way. So this correlation is around 0.66. Yeah, so this is something we'll come back to when we talk about artifacts. So we can also look at standardized mean differences. So a motivating example for standardized mean differences is gender differences in agreeableness. So one of the big 5 personality traits, the big 5 are agreeableness, openness to experience, conscientiousness, extroversion, and neuroticism. One of those is agreeableness, and it tends to be the case that women, on average, score higher. And we see that in this sample, there's a standardized mean difference of around 0.45. So again, these are just example data sets that will be used for the actual artifact corrections. Then we can talk about effect size errors. So there's 3 components to a study estimate of an effect size. You have the target population effect size, which is the effect size between the random variables of interest in the population of interest. But then you have random errors. So this is sampling errors. So upon repeated sampling, effect sizes are going to differ. So in this plot, we show the sample ID on the x-axis, the effect size on the y-axis. The blue points are the fixed population value of the effect size. The estimate for each sample is the black dots. And then you have error, and that error is random. So for us, random error is unpredictable, so we're not going to be able to really correct for sampling error other than just increasing the sample size. And so the variation in effect size estimates across samples is known as our sampling variance. And it doesn't have to be normal, but I just use that as an illustration. So there's also systematic errors. So these are errors that are consistent across samples. For instance, if we were to take the correlation between, let's just say the correlation in the target population, but the correlation between a proxy variable for X and a proxy variable for Y. So these proxy variables have measurement error. And then you can relate that to the target population correlation on the random variables of interest by this sort of arbitrary factor we'll call the artifact attenuation / inflation factor. So it's a multiplicative factor that pretty much allows us to relate the target population correlation with the study population correlation. So we can define the artifact attenuation factor as sort of the ratio between the observed or the study correlation and the true or target correlation. So with systematic errors, upon repeated sampling, if the effect size estimate is unbiased, if the estimator is unbiased, then we should see no difference between the mean of across samples and the target population value. Now, if it's attenuated, that means that the estimates are driven towards the null, which in this case for both correlations and standardized mean differences is 0. And then it's inflated when it's driven away from the null. So combining these errors and the target population correlation, or the target population effect size, we can relate, we can talk about the observed effect size as being a product of the target population effect size, systematic error, and random sampling error. And so those are the three components that we are going to be modeling essentially the entire book off of. Now, the one that we care about the most about is systematic error. So systematic error is predictable. It allows us to actually be able to make corrections, whereas random error is unpredictable and we can't really correct for it unless we were to actually like increase the sample size or the precision of our estimator. So the first artifact, you can consider it an artifact, but this is just a property of an estimator essentially. So is a small sample bias. So small samples can cause average differences between the population effect size and the sample estimate. And that's true for both standardized mean differences and correlations. So if you look at the first plot here, this is the standardized mean difference on the y-axis and the sample size on the x-axis. So as you lower the sample size, you'll see that the bias, which is darker blue, increases in small sample sizes. And it also increases when this estimated standardized mean difference is larger as well. So if you have a standardized mean difference of 1, you'll see some small sample bias, but if you have a standardized mean difference of 0, you see none. So it's a multiplicative sort of relationship. So the correction here is often referred to as Hedges correction, Hedges G, which is takes that small sample bias and corrects for that sort of difference. And this is what I described here. Here's an example that I'll probably just skip because it's just a small sample effect size, and then we can correct it. It goes from 0.78 to 0.75, but I'm going to skip past that one. So the correlation coefficient also sees small sample bias, albeit the small sample bias in the correlation is much smaller than the bias in the standardized mean difference. And that's why you probably don't hear about it as much as like Hedges G. But yeah, in small sample sizes, the estimated correlation is biased. However, even if you have a sample size of like 5, the bias reaches like a maximum of 0.1. So, and the bias here meaning the difference between the expected sample correlation minus the population correlation. So there's very minimal bias, and you probably don't have to correct. And also the correction is extremely complicated. It's like a hypergeometric function. Yeah, you probably don't have to use the Pearson correlation correction in practice that often. So yeah, now at the end of each section, I have R code with real data. So each section, each chapter will have how to calculate like the artifact correction in R using packages like Metaphor, Psych Meta, Psych, and a few other packages. And each box like this, where you have like the height and weight fake data, this entire box is computationally reproducible. So you could copy and paste the script, all the code in this box, put it into an R script, and it should run. If it doesn't, then I would probably make a comment or an annotation. So our next sort of like 4 chapters is describing measurement error, construed broadly as any difference between the random variable of interest and the observed proxy variable that we have in our study. The first type of measurement error we're going to be talking about in the case of continuous random variables, that's going to be classical measurement error. So classical measurement error here, we're talking really about a sort of form of classical test theory, where the expectation of observed scores over repeated measurements for a person is their true score. So if I were to take a reaction time test, if I do an infinite number of trials, the average across those infinite trials would be my true score. So that's essentially the assumption you kind of have to make if you're doing these sort of corrections in this chapter. So this chapter kind of goes over reliability, reliability of composites, so composite variables that are made up of multiple sub-measurements. And so this image, for example, you have sub-measurements on the x-axis, you have the score on the y-axis, you have the true score here, and you see that in a low reliable composite measurement, you have a lot of variation between sub-measurements. Same, or the opposite is true for the high reliability measurement. But yeah, so the composite score, which is the dark dots here, the confidence interval is much larger for the low reliability and much smaller for the high reliability measure. Yeah, so then we go over how to calculate like coefficient alpha, some split half reliabilities, and I have some R code for calculating the reliability of mean scores or sum scores, and also how to calculate it from a correlation matrix, so from raw data and from a correlation matrix. And then we talk about Mosier's reliability, which is a type of composite reliability that has actually certain advantages compared to coefficient alpha, and then how to calculate that number. Then we can talk about coefficient of stability, so like test-retest reliabilities, which essentially takes 2 sets of observed scores at different time points and correlate them. A low stability test or measurement will have a low correlation between time points. High stability will have a high correlation between time points. And so you can see the change across time points in the observed scores for the low and high stability. So let's look at how a reliability or how measurement error impacts correlation coefficients. So in the top left figure here, we have the true score correlation, so the correlation between the 2 random variables of interest for x and y. We see that the correlation is 0.5. However, if we were to measure x and y with imperfect measurements, let's say that the reliability of the observed score of x is 0.8 and the observed score of y is 0.8 as well, then we'll see that the distribution, the joint distribution, is a little bit noisier, and that noisiness will reduce the correlation, so it'll attenuate the correlation. So if we were to just fix the reliability of y as perfect, so there's no unreliability in y, and we just change the reliability of x, we'll see that the observed correlation goes up to, and at 1 is the true score correlation. So you'll see as you increase reliability, you'll increase the observed correlation. And of course, if reliability is 0, then the observed correlation is also 0. So if you were to take the reliability of X and the reliability of Y and map it out, where the dark pink is the observed correlation. So like the dark higher observed correlation is a darker pink, lower is lighter pink. So you'll see that when reliability of X and Y is perfect, yeah, at 1 on each point, the observed correlation is 0.5, which is our true score correlation. And as you reduce the reliabilities, you see that it goes down. So that's actually one of my favorite figures, by the way. So there's some R code for correcting correlations, also bootstrapping corrections, because one of the issues with a lot of these corrections is that they assume that a lot of the artifact values, like the reliability coefficient, are fixed, which or known, and they often aren't. So sometimes it's better to do some sort of bootstrapping procedure, which will require the raw data unless you do a parametric bootstrap. But I have the code for that in this. Also, now I kind of snuck in an assumption. I didn't really make it obvious, where the errors, the measurement errors in the X variable have to be uncorrelated with the Y errors in order for that correction or that reliability relationship to actually make sense. So, but you could have differential measurement error where the errors are correlated between X and Y. And in that case, you have a different correction procedure, which requires the correlation between the errors of X and Y. So same thing is true for standardized mean differences, where less reliability, lower reliable scores are going to attenuate the effect size. So if we look at the true score distributions of two groups, you'll see that it has sort of a narrow shape to them, narrow variance. And then you look at the observed scores, you see that the variance increases, but the means stay the same. So when you have classical measurement error, you'll see that the means are identical for observed and true scores, but what makes them different is the width of the distributions. And because the standardized mean difference divides by the within group standard deviation, that means that if you increase the standard deviation, you lower the standardized mean difference. So the mean difference actually is an unbiased estimate, even in context of classical measurement error. So misclassification is a type of measurement error we see in Bernoulli style or Bernoulli random variables that take on a value of either 0 or 1. So for example, let's think of two clinicians rating the same sample or classifying individuals into either having major depressive disorder or not. And so those two individuals do their ratings, they're blinded to each other. And then we tabulate the scores. We calculate a contingency table, and this is what it would look like. So imagine this is clinician 1, G prime, and then clinician 0 or whatever, 1 and 2 maybe. You'll see that the agreement will be on the diagonal. So if they both think that the person does not have the major depressive disorder, the diagnosis, if they agree on the diagnosis, then they'll be on this diagonal. If they don't, they'll be on this off diagonal. And so from that contingency table, you can calculate what's known, what I guess I call as a classification reliability, which is really the correlation between the classifications of each rater, or of each clinician, or observed random variable. So the correlation between the two sets of diagnoses would be the classification reliability. So a higher reliability, which would mean that there's more agreement between the two parallel classifications. And you can use the classification reliability to correct both the correlation coefficient and the standardized mean difference. And so we pretty much do that down here. Oh, sorry, not the correlation. Just the standardized mean difference. This section is really exclusively for the standardized mean difference. So this visualization just shows a group difference between red squares and blue circles. And so we see in this first figure that all the red squares are properly assigned to group 0, and all the blue circles are properly assigned to group 1. If we were to randomly misclassify individuals into both groups, what you see is that the means of the two distributions start to converge, and the variances of each distribution expand as well. So both of those things combined is going to attenuate the standardized mean difference. Now, this is especially for the case of non-differential misclassification. So you could have, so non-differential misclassification means that the misclassification is completely random and not correlated with the outcome. So if it was correlated with the outcome, you actually might not see any attenuation. But this is, yeah, again, assuming random misclassification. And here's a code block with the classification correction, or the misclassification correction. The next chapter is on artificial dichotomization. Essentially, artificial dichotomization is taking a naturally continuous variable and then dichotomizing it into two groups. You have low scorers and high scorers. So we can correlate the dichotomized score with the underlying continuous score, and we'll see that the correlation is less than 1, which you would expect that if you correlate a variable with itself, it should be 1. But because you dichotomized, you're losing information, and you're adding measurement error into the correlation, into the variable. So what does that do to a correlation coefficient? So if we were to assume, let x and y be like a bivariate normal distribution, like this. So if we look at the continuous x and continuous y distribution, we have a nice correlation of 0.5. And then if we were to dichotomize x, that correlation drops slightly to 0.41. And if we were to dichotomize both x and y, then that correlation drops even further to 0.33. Artificial dichotomization, if we assume a underlying normal distribution, will attenuate the correlation. Now you could get some, if you had like a wacky sort of underlying distribution, you actually could have an inflation, but I think for many cases, you'll see an attenuation in the correlation. I skipped one aspect of the effect size that was an example of social. So this is an example of dichotomization. Now I put this in the effect size section on the effect size chapter, but it should probably be in the dichotomization chapter, but I did that just for, it's a motivating example for artifacts generally. So imagine you had a sociability score. So you had a sample that filled out a survey relating to sociability, and you dichotomize them into social butterflies and wallflowers. So I'd probably personally be a wallflower. And then let's just say, so that was like cut from the median split. So the median split defines social butterflies and wallflowers. So if you look at the correlation between sociability and impulsivity, we'll see a correlation of 0.39. So the correlations are down here in this table. See a correlation of 0.39. Now, when you dichotomize, even though it's not perfectly a normally distributed variable, but when you dichotomize, you see an attenuation to 0.31. Now, after correction, so with a median split, you generally see assuming a bivariate normal, you see a attenuation of around 20%. So if you sort of reverse that, then you can get the corrected effect size of 0.38, corrected correlation of 0.38, which more closely reflects the original scale. So let me go back to this. So yeah, this illustration right here just is an illustration of bivariate dichotomization. So you essentially, if you dichotomize both x and y, you essentially are making a contingency table with sample sizes in each quadrant of that dichotomization. So the next artifact is scale coarseness. Now, scale coarseness is related to artificial dichotomization, particularly if the coarseness of the scale was essentially two scale points, then you'd have dichotomization. But imagine you had a liquid item, which is let's say a 5-point or 7-point liquid item, or in this case, we'll say a 5-point liquid item. But the underlying thing that it's measuring is continuous. So we can relate the coarse score, the 5-point score, to the continuous scores, and we see that the correlation isn't perfect, even though it should be because it's the same variable. But coursing the scale will add additional measurement error to the correlation. Now, this is assuming that the scales or the intervals between scale points is equal. So if we were to take another bivariate normal correlation between continuous x and continuous y, and then we were to coarse the x scores and leave the y as continuous, we see a slight decrease of around 0.03. So one thing is that obviously there's an arbitrary number of scale points. So this example is just 5 scale points, but we'll see how having more or less scale points might affect the correlation. And then the last figure here is coursing the x variable and the y variable. And you see an even lower correlation of 0.44. We'll see that. So on the different scale points, these are the continuous coarse score correlations. So essentially this correlation, but with varying number of scale points and 2 different types of underlying distribution. So if the distribution is normal, you look at this column. If the underlying distribution is uniform, you look at this column. So with more scale points, you'll see that the correlation increases between continuous and coarse scores. And same thing is true for the uniform underlying distribution. Now, really beyond, I'd say beyond, honestly, like 9 or 10 scale points, it really doesn't make much of a difference. You start seeing pretty much no effective coarseness beyond 15. So this is really meant for small scales or with very, very coarse scales. But you can use these correlations to actually correct the effect sizes. So whether that be the correlation coefficient or the standardized mean difference. And we have some more examples for that. And then I think I like these chapters the most, but the indirect, so we have 2 types of selection effects. We have direct selection and indirect selection. So direct selection occurs when we are selecting individuals into our sample that are above some or below. I mean, you're selecting a subset of the population based on some interval of one of the variables of interest. So, for example, if we look at the SAT and ACT correlation of 0.66, let's say we look at a sample that's from an elite university where their SAT scores have to be a minimum of like 1200 or something. So any score above 1200 is included in the sample, but any score below 1200 is not included into the sample. So you'll see that the correlation drops a lot from 0.66 to 0.43. So that's sort of a real world impact of, and you see this a lot in college admissions testing where SAT scores and GPA are only looked at within the sample of college students who have already been selected to get into college, selected on SAT and GPA. Well, that would be more applicable for the indirect selection section. But so univariate range restriction would be if you were to take like the upper half or like the lower half or some interval of one of the variables of interest. So we'll take x above, some value here, included into the sample. That will attenuate the correlation coefficient. However, so yeah, the correlation here, the true correlation is 0.5, and the correlation in the blue dots is 0.39. So, but we can also see a univariate range enhancement, which means if you were to take out the individuals in the middle of the distribution, you would actually see an increase in the correlation because you are increasing the variance by sort of extending that distribution. So that's going to have an opposite effect than range restriction. So this can also happen on both variables. So you could have range restriction in X and Y, directly on X and Y. So you take people above a certain value of X, take people above a certain value of Y, and you'll see even more attenuation in the correlation. And then you could have a pretty wacky scenario where you'd have bivariate range enhancement, which means you would take the middle out of X and the middle out of Y. However, I don't think I've ever seen anything like that in practice. So, but it's in principle, it increases the correlation. by a lot. Yeah, and then the last chapter of artifacts is indirect selection. So indirect selection occurs when you're selecting people into the sample based on the on some other variable of some other variable not of interest. So if you're correlating X and Y, you're selecting on some third variable Z or something. So back to the SAT and ACT example, if we were to look at the quantitative scores for the quantitative subtests of the SAT, correlate that with the ACT, we can see what it would look like if we were to select on the verbal subtest of the SAT. So even though we're not selecting on the SAT quantitative or the ACT directly, we're selecting on a third variable that's correlated with SAT quantitative and the ACT. So what happens is you see a drop in the correlation from 0.61 to 0.31 to 0.34, which is a pretty drastic attenuation. So you'll see this sort of fuzzy selection where if I were to select on a variable, some third variable Z that's correlated with X, then you'll see that on average, the individuals in the low end of X are excluded here, but it's fuzzy. So it's a fuzzier boundary than direct selection, and it's probably more realistic. So if we talk about college admissions are more holistic than just the SAT score. So you won't find it won't be like a direct selection problem. It'll be more of an indirect selection problem, where the admissions selection is correlated with SAT, but not 100% correlated. Then you can also have range enhancement here as well. So if you take the middle of some third variable Z, and that third variable Z correlates with X, then you can have some indirect range enhancement. You can also have it be both. So with a univariate indirect range restriction or selection, when I say univariate, what I mean is that Z is directly restricting range on X or enhancing range on X, and any restriction or enhancement of range on Y is completely mediated through X. That's what it means by univariate restriction. But bivariate restriction means that Z has independent effects on both X and Y. So in a case like this, we're actually selecting on a confounder of X and Y. If I select on a confounder of X and Y, it means Z has direct relationships with X and Y. And so if I select on Z, then I'm going to have this sort of, you can kind of see like there's like a plane right here where Z is selected. And because they're both correlated, anything beyond this sort of diagonal thing is included. So yeah, and then that's probably that's a very realistic example of I think admissions assessments. You can also have bivariate range enhancement. This is another case where I don't see that ever happening in practice. I mean, I don't know what sort of thing that could make that happen, but in principle, if you did have bivariate indirect range enhancement, you'd see a big increase in the correlation. So then the last section, which I think I need to do more on, is the meta-analysis section. So how do we apply artifact corrections to our meta-analyses in order to get better estimates of our target effect size? Yeah, briefly, like this is a diagram of a common effects meta-analysis where essentially effect sizes are all estimated in a single population value. Random effects meta-analysis is that the effect sizes from each study are actually coming from multiple population effect size values, and your mean of those effect sizes is the estimate of the mean of population effect sizes. But essentially, artifact corrections are going to allow us to reduce the heterogeneity in population effects that are due to sort of spurious between study factors, like different studies have using different scales with different reliabilities, or they have different levels of range restriction. Using artifact corrections can actually reduce the heterogeneity across those studies. It can also help better estimate the target effect sizes of interest. And then I have a conclusion chapter, which is just concluding remarks. Yeah, in the future, I have a lot of ideas of features and additions I want to make, but I'm also open to many suggestions as well. So that is it.
Thanks so much, Matt. Wolfgang just asked a question. He said, just wanted to say that the overall design of the book and the visualizations are really fantastic. For an actual question, what do you think about the idea of using artifact distributions for corrections as described in the H&S method?
Yeah, so actually, I don't have a section on artifact distributions because I think it limits your ability to do moderator analyses because you have to meta-analyze first the artifact value, so for like reliability or U ratios for range restriction. And then once you meta-analyze each of the artifact values, then you make the correction, which you can't really do that for moderator analysis. So it kind of limits your ability to do that. Also, there's a lot of assumptions that come into play when you do artifact distribution models, like dependency of artifacts, which usually, poor studies are poor studies across the board, not just with reliability, but high quality otherwise. Um, so I have some ideas of like imputation strategies for missing values. Because artifact distributions allow you to do these corrections when there's a lot of missing reliability estimates across studies or U ratios. So I think I want to talk more about imputation strategies and doing individual correction methods, meaning um, corrections within each study rather than meta-analyzing and then correcting. So yeah, my opinion is that we should probably focus on individual correction and try to do our best to impute missing artifact values.
Nice. Yeah. Anybody else? Yeah, sure. Isabella, go right ahead.
Excellent talk and work, Matthew. I'm a huge fan. As you were talking about this, I sort of started visualizing this cube in my mind, which had three axes. The vertical axis was who gets basically measured, the individuals. Then one of the horizontal axes was what variables, and then the third one was sample size or data. And it kind of struck me that, these artifacts are all about having less information on the individuals because you're focusing on a particular slice of the population that maybe you shouldn't get obsessed with. Also the variables you're measuring less because you're working with a proxy or you're using a coarser scale, and the sample size, if it's too small, if you include too few individuals in your sample, that too causes problems. So I think all of this work could probably be captured within the cube, who, what, and sample size. So I'm curious, like, do you only correct for one artifact at a time, or do you correct, for a kind of a multitude of artifacts, or should you correct for a multitude of artifacts? And also, I would like to suggest maybe like check mark for the book, things that people can do at the design stage to sort of prevent the need for correction if
Yeah.
possible. Like, use a scale with at least X many um, items, or, use several proxies, not just a proxy or whatever. Like, how do you move people from less to more? And I think I'm going to squeeze one more question in here. I'm
I'm
not
asking
quite
repeat the first one, but
yeah, I'm not quite clear like on the artifact correction, like how do you bring all of this in? Like, can you include, do you correct just the actual effect estimate, or in your model, with Hedges correction or whatever, or in your model, can you sort of allow for different components of the model to pick up that correction? So that's about it. I
yeah.
thought it's easier to ask.
So for the first question, and I'm gonna probably forget the other two, but so for the
Mhm.
first question, was can you combine multiple different artifacts? So like if you had
Mhm.
poor reliable measurements and you had selection, and a bunch of other things, you
Mhm.
definitely can. And so you have to be careful with how you do it. So like with dichotomization, and let's say you dichotomize scores that already were low in reliability to begin with, you can actually, with assumptions, you can correct multiplicatively. You can do the dichotomization correction and the reliability correction in one go. With the direct selection and indirect selection, it's much more complicated, but you can do it. The one problem is like, so I'm going to show you like the equation for like combining. Like this is like the equation for combining like reliability with direct selection, or maybe this is indirect. I don't know. But the issue is that you have so many estimates in this equation that now you're blowing up the sampling variance too. So that's something you have to keep in mind, because the correction procedure also has error. And so now when you have so many artifact values in here that are all estimated, you have to also adjust the sampling variance. And when you have more complicated ones, honestly, like bootstrapping is like the only way to really capture all the variance. But in principle, you can correct all those things. Second question. Oh, sorry. Yeah. So second question was having a section on trying to stop this at the design phase. For sure. I think that's a good idea. I think a lot of these though are things that are hard to do in the first place, like hard to stop in the first place, because like no matter what, reliability is not going to be perfect for most things. No matter what you do, it doesn't matter if it's like the best scale ever, it's still going to be unreliable to some degree. And you can't get a simple random sample from the population, and sometimes it's unethical to do so. So some things are going to be more difficult to adjust the design phase, but yeah, for sure, I should have a section on that probably.
Yeah, and I just to interrupt, I think that cube should actually have a fourth dimension. So one should be sample size at the end, and the other should be data, because you talked about data missingness too. So that's again having less information. So that theme of
true.
Yeah, having less information is kind of a recurring theme.
Yeah. So another thing is like you can a lot of these corrections you can do if you have the raw data like better. Like so with the correction for measurement error, for example, if you were to do like a structural equation model, you might have a better you might do a better job at actually correcting the correlation. So a lot of it comes down to like, do you have access to the raw data? And because we're all, most of us, or some of us are meta-analysts, that we generally don't have access to the raw data. So you could do more fancy things that are better, which I should probably include some of those things if the raw data is available, how to make those corrections better, how to capitalize on the raw data. But a lot of these corrections are based on, after you have the effect size estimate, how do you correct for? Yeah.
Good, thank you. Yeah, and the last curiosity I had before someone else needs to ask is, how do you know the bias is multiplicative or additive?
Yeah, good question. So with that sort of original model where you have a multiplicative,
yeah, with the correlation coefficient, it was multiplicative in one.
I use a correlation as an example, but it can be true for really anything. So the multiplicative, so these are really arbitrary. So like the alpha is like really like just at this point of the book, it's a completely arbitrary value. So technically you can structure alpha you can define alpha in a way that would be a additive attenuation. So like I put it there because I put it as like a multiplicative factor because a lot of the corrections are multiplicative. I think actually all of the ones in the book is multiplicative, so it just makes it easier.
So the question is by Vilgot. I'm sorry if I got your pronunciation wrong. So he says, or under what conditions is it appropriate to use artifact corrections? For example, correcting for reliability when reliability is too low looks a bit fishy to me.
Yeah. So I mean, obviously, if you have like a reliability of 0.2, it seems kind of silly to correct, and you also run into problems where it's like if the reliability is smaller than the correlation, then you end up you end up like getting a correlation of over 1, a corrected correlation of over 1. And actually, I think in Spearman, his like article where he first introduced the correction for attenuation, he actually calculated the correlation between like sensory discrimination and like teachers' ratings of intelligence as like over 1. And so you can run into those problems. Now, the thing is that keep in mind is like the variance also changes too. So like this isn't like you don't get a free lunch if you make these corrections, because not only is your estimate goes up maybe by a lot, but the more it goes up, the more variance that the estimator, or the more variance that the corrected correlation or the corrected effect size has. So in a meta-analysis, it's going to be weighted a lot less. So yeah, it is sketchy. And that's why you also want to assess for methodological quality in meta-analyses as well, which could weed out some of those types of problems. But I also don't think that a lot of studies would report a reliability of like 0.3 or 0.4.
Can I ask, do you have like a rule of thumb for when it's too low to consider correcting, and when it's more just throw it out? Or
I think so. Granted, the assumptions are true, like it works fine. If the assumptions are true, then the correction works fine no matter the correlation. So I would say that, like, I don't know, it's like the same kind of problem if you see some study reporting a standardized mean difference of like 9 or something like that. It's like, do I trust it, or like what should I do? One solution that's possible is using I talked to Brenton Wynick about this, or Wernick. He had suggested to me that like you could use best linear unbiased predictions for the artifact values for each study. So instead of using the raw value, you use like the predicted. So if you took a random effects model and you took the predicted value, which makes all the estimates a little bit closer together, doing so would increase the reliability. So you can do that for the artifact values. So like if you did the reliability coefficient, it would sort of drag the reliability coefficient closer to the mean reliability coefficients, which might make it a little bit better. But otherwise, like the correction is given the assumptions that are.
yeah, maybe it's that low reliability should make one question the assumptions rather than.
Yeah, for sure. Yeah, and yeah, I mean, classical test theory assumptions that I introduced here are quite strict. So it's like they might not work for your given research goal. So
Thank you.
So just to follow up on Vilgot very quickly, do you suggest or would you recommend that people report results with and without artifact corrections so that they can get a sense of how much the correction will reduce the bias but increase the variance type of thing?
Yeah, I would say that pretty much every study should have the raw values for sure. I mean, they should have the raw data. So I mean, my suggestion would be every study would just make their data open access. So, but yeah, if a study wanted to correct for it, a lot of these artifact corrections are really done at the meta-analysis level. But because you can do probably better corrections if you have the raw data. So within a study, maybe the authors probably choose to do some sort of structural equation model instead of doing the correction for attenuation I have here. So yeah.
Thank you so much again for presenting to us. I mean, your visualizations are off the charts.
Thank you. I appreciate that.
All right, well, thanks everybody, and hope to see you next month.